Naturally aspirated engine makes power, and it was the standard for decades before boost systems became common. Air enters the engine only because of atmospheric pressure and the movement of the pistons pulling air into the cylinders. There is no compressor forcing extra air inside. Because of that, naturally aspirated engines deliver smooth throttle response and a very predictable power band. Older sports cars, classic muscle cars, and many racing machines relied on this setup because it feels direct and mechanical. Even today, many drivers still prefer the instant response and natural engine sound that comes with no boost whatsoever.
Turbocharger. A turbocharger uses the engine's own exhaust gases to spin a turbine connected to a compressor wheel. That compressor forces more air into the engine, allowing more fuel to burn and creating much more power from a smaller engine. Turbocharging became extremely popular during the fuel efficiency era because manufacturers could replace large engines with smaller turbocharged ones while keeping similar performance. The downside is something called turbo lag, that brief pause while the turbo builds pressure before the power hits. Modern engineering has reduced this delay a lot, but the feeling still defines how many turbocharged cars behave.
Single turbo. This is the most common turbo setup found in modern cars. One turbocharger handles all the exhaust flow from the engine. Smaller single turbos spool quickly and give strong low-end power, while larger ones create massive top-end horsepower but respond more slowly. Many daily drivers use compact single turbos because they balance efficiency, simplicity, and cost. In high-performance builds, larger single turbos are often chosen for huge horsepower numbers, especially in drag racing and the street tuning scene. Twin turbo. Instead of relying on one turbocharger, this system uses two. In V-shaped engines, each turbo often handles one side of the engine separately. Smaller twin turbos spool faster than a single large unit, giving smoother power delivery across the rev range. Luxury performance brands helped make twin turbos famous because they offered both strong acceleration and refined driving manners. Some supercars also use this setup to produce enormous power while keeping response sharp and controllable. Sequential turbo. This setup uses multiple turbochargers that work at different engine speeds. A smaller turbo operates first for quick low-end response, then a larger turbo joins in at higher RPM to provide more airflow and stronger top-end power. The transition between the two turbos can feel dramatic depending on tuning. Sequential turbos became well-known in Japanese sports cars during the 1990s, where engineers tried to solve the old problem of balancing turbo lag with high horsepower. Twin-scroll turbo. Inside a normal turbo, exhaust pulses can interfere with each other and reduce efficiency. A twin-scroll turbo separates those exhaust pulses into different channels before they reach the turbine. That design improves spool time, throttle response, and overall efficiency without needing a second turbocharger. It became especially popular in modern performance cars because it delivers better low-speed response without the complexity of a twin-turbo setup. Variable geometry turbo. This turbo changes the angle of internal vanes inside the turbine housing, depending on engine speed and exhaust flow. At low RPM, the vanes narrow the passage to speed up exhaust gases and reduce lag. At high RPM, they open wider to prevent restriction. Diesel engines adopted this technology early because diesels naturally produce strong exhaust pressure. Over time, improved materials allowed some gasoline engines to use variable geometry systems, especially in high-end sports cars. Electric turbos rely completely on exhaust gases, but electric turbos add an electric motor to help spin the compressor instantly. This nearly eliminates turbo lag because the boost can begin before exhaust pressure builds up. As hybrid technology grows, electric turbos are becoming more practical in performance vehicles. They represent a bridge between mechanical turbocharging and electrically assisted power systems. Centrifugal Supercharger. Unlike a turbocharger, a supercharger is driven directly by the engine itself rather than exhaust gases. The centrifugal design works somewhat like a belt-driven turbo compressor. It builds boost progressively as engine RPM rises, creating a smooth increase in power rather than an instant hit. Many aftermarket builders use centrifugal superchargers because they are relatively compact and easier to install than other supercharger types. Roots Supercharger. This is one of the oldest supercharger designs. Large rotating lobes force air directly into the engine, creating immediate boost even at low RPM. The result is instant throttle response and massive low-end torque. The large blower sticking through the hood of classic American muscle cars is usually a Roots supercharger. It became iconic in drag racing because of its aggressive appearance and brutal acceleration. Twin-screw supercharger. This design compresses air internally between two meshing screws before sending it into the engine. It runs cooler and more efficiently than a Roots blower, while still delivering immediate boost response. Twin-screw superchargers are often found in high-performance street cars, where both strong power and drivability matter. They deliver a thick wave of torque that feels strong across almost the entire RPM range. Electric supercharger. Instead of being belt-driven, this system uses an electric motor to compress incoming air. Because it does not rely on exhaust gases or engine speed, boost can arrive extremely quickly. Some manufacturers use electric superchargers alongside turbochargers to improve low-end response before the turbo fully spools. This combination is becoming more common as vehicles move toward hybrid and electrified powertrains. Compound boosting. This setup combines a turbocharger and a supercharger in the same engine. The supercharger provides instant low-end boost, while the turbo takes over at higher speeds for greater efficiency and power. The result is a very wide and powerful torque curve, though the engineering becomes far more complex. Some famous rally cars and high-performance builds experimented with compound boosting to achieve both rapid response and extreme horsepower. Nitrous oxide injection. Unlike traditional boost systems that compress air continuously, nitrous oxide delivers extra oxygen. When injected into the engine, it allows more fuel to burn and creates a sudden increase in power. Nitrous became famous through drag racing and street racing culture because it is relatively simple and can produce dramatic results almost instantly. The effect usually comes in short bursts rather than constant operation, which gives it a very different character compared to turbochargers or superchargers. Ram air. This system uses the vehicle's forward motion to force more air into the engine intake at higher speeds. It does not create boost in the same aggressive way as a turbo or supercharger, but it can slightly increase pressure and improve airflow efficiency. Ram air systems became especially popular in performance cars and motorcycles, where high-speed airflow could be used to real advantage. The design also helped create some of the large hood scoops seen on classic performance vehicles. Roots Supercharger. This is one of the oldest supercharger designs. Large rotating lobes force air directly into the engine, creating immediate boost even at low RPM. The result is instant throttle response and massive low-end torque. The large blower sticking through the hood of classic American muscle cars is usually a Roots supercharger. It became iconic in drag racing because of its aggressive appearance and brutal acceleration.